Thank you for joining to watch and listen my lecture on cross-sections and line broadening, and of course the course is laser physics. So what I want to say here and why we are having this lecture now is that we want to move in our mathematical treatment of basically concerning just single atomic absorbers and emitters into a more realistic scenario of a medium consisting of like millions or billions of emitters, and we want to understand really how, for example, like a kind of macroscopic laser medium behaves. So that's why we need to start moving in our treatment from individual emitters into a bunch of emitters and absorbers. And basically now we are showing you how the mathematics can be generalized, and then subsequently how we can start having a kind of like new concepts emerging. So essentially the kind of like line broadening mechanisms start arising in our piece of mathematics. So we want to go basically in our treatment from a single atomic emitters into a bunch of atomic emitters to understand how really a kind of macroscopic gain medium behaves. So I will now get into the actual business. So what we can do next is that we can calculate the absorption cross-section for a two-level system. And this is essentially very similar that we already did for the case of a stimulated emission. So sigma, essentially how that kind of conceptually is understood. What is the cross-section for absorption? It's basically the power absorbed divided by the impinging intensity of light. So essentially, mathematically, this is, and if we approximate the time derivative for the expansion coefficient CE to be just a 1 of that term over t, and then the impinging intensity is noted with I naught. So then this is basically what we are saying here. So power absorbed and then impinging intensity, and then we can calculate things. So that would be basically kind of like pi times E squared times the impinging field's amplitude squared times mu absolute squared. So essentially the dipole moment divided by 6 times h bar times the intensity of the impinging field. And then we have this Dirac delta function there regarding the laser transition. So we need to really be hitting the right laser transition for things to happen. So basically for light to be absorbed. Now introducing the photon flux F, and this would be more like a kind of macroscopic quantity that can be written that's the kind of like h bar times omega, angular frequency of light, times the intensity. We can really define that the kind of amplitude squared of our impinging field is 2 times divided by the vacuum permittivity epsilon naught times the speed of light times the refractive index of the macroscopic medium, and then we integrate this kind of like a radiative energy density associated with the field plus the thermal bath we have the gain medium inside with, and we integrate over frequencies. So this is basically defined that's the 2 times of flux divided by epsilon naught, the vacuum permittivity times the speed of light times n. And here the unit for the photon flux is essentially number of photons per second per square meter. So essentially per kind of like cross-sectional area. Now we can note that the F over I naught is essentially h bar omega. We can really write the absorption cross-section in a way that the sigma that depends on the frequency is a 2 times E squared times the dipole moment squared, and then 3 times epsilon naught times speed of light n times n, speed of light times the refractive index n times the reduced Planck constant h bar, then the laser transition frequency omega naught times a delta function, so that there's something happens when we are hitting at the right frequency our substance. The units for absorption cross-section, they are meter squared divided by the number of photons, and this is of course compatible with the previous notation, so that the rate of absorption W equals sigma times F, the photon flux. And then here we can see that the units for this rate of absorption are the inverse seconds. And this is basically what we were using before in the equations. So this is basically what we get out. So here we place in this into here, and then we note that okay, F I naught is basically this, so we can land with this equality. So nothing strange there, basically. The thing here is that this is basically mathematics concerning a single atomic absorber and subsequently also emitter. And we want to really move into a system that we have a bunch of these kind of emitters and absorbers within the medium. So we really need to generalize our treatment into a multi-atomic system. So we really basically want to understand how macroscopic media are, and we want to consider effects that arise from this fact that the medium is actually made up of a collection of atoms. So for example, if it would be treating a gaseous medium, those individual gas molecules or atoms, they could be moving at a given speed, velocity dictated by the temperature of the environment, and that speed may, through a Doppler shift, give rise to a bunch of different frequencies that actually are resonant within the impinging field. So these are, for example, the effects that take place. Or similarly, in a solid state, we may have phonons, broadening distributions, or we also may have like kind of crystalline local field effects that also smear the laser transitions. I guess more of this on the discussion exercises to understand how things work out. So please, let's now do the kind of mathematics so that we can really understand what happens when we are generalizing this math. And we start by recalling that the absorption cross-section that we have dealt with now is really an average area, basically, of a single atom. So that's the kind of geometrical interpretation. What's the kind of meaning of absorption cross-section? So if we have a photon incident on the medium, and that illuminates an area of sigma, then this photon will be absorbed by this atom. And now looking at the kind of like population of collective ground state, and that the population is given by, of course, Ng. And here it's really worth noting that this Ng, what are the kind of units, how it's being defined, it really corresponds to number of atoms per unit volume. Sorry, I have a typo there. It should be volume here. So this is really the kind of quantity of interest. And this really is being then connected with the geometrical interpretation of the cross section. So, but let's bear with me for the next slide. So the fraction of flux absorbed by a thin slab of a medium. And now we are looking at the kind of like a thin slab of gain medium, and we want to understand how that behaves in a kind of macroscopic manner. We have laser light, or our pump is shine into that medium, and we want to understand how it's being macroscopically absorbing this light. So the fraction of flux absorbed by this thin slab of a medium is really the fraction of area effectively filled by these atoms. So we can really, based on these kind of geometrical considerations, we can write this equality so that the fraction of flux delta F divided by F, so that's the fraction, equals to a kind of fraction of area ds per s. So how much of space these emitters are taking out from this thin slab of a medium. So S is the cross-sectional area, and then ds is essentially number of atoms in this cross-sectional area times the area occupied by one atom. So this is basically how we define this. And we have how many atoms we have in this one cross-sectional area of interest, and then what is the area that is occupied by one atom. So that's kind of like how we calculate things. And now recalling how we are defining things. So essentially now we can write that this equals to the population. So this was the kind of number of atoms per unit volume. We have a cross-sectional area here. We have the kind of differential length interval here. So that would be the volume. So that basically gives us N1 times S times dz, gives us basically the kind of like atoms in this cross-sectional area, thin slab of our medium. And then we have this sigma, the area occupied by one atom. So now we get this equality by just considering the kind of geometry of things in our system. And now we can write that the kind of differential of the photon flux dF equals minus F times sigma times N1 times dz. And this basically equals minus W, the rate of absorption, times N1 times Z, by using the previous notation for the rate of absorption. So this is basically that we were using here. And the units here would be absorption rate per unit volume for this WN1 term. So what we see here is that we are now having means of understanding how the medium behaves macroscopically. And we really want to understand how the system behaves with respect to W, because this is ultimately the kind of like a parameter we can easily plug into differential equations that then tell us about the kind of rate equation. So basically the kind of like a dynamics of our system. So we really need to care about the kind of W, but we should also remember that this has origins in the kind of like microscopic treatment. So essentially we have these origins in sigma. How do we calculate this W? So now we are kind of like wanting to make this transition so that what happens when we actually have a bunch of atoms forming the actual medium, and the medium's response, the medium's absorption rate is then being like described by more of this kind of macroscopic quantity. So in a way, like we move now from this kind of treatment of our light matter interaction using this microscopic quantity into the treatment using a macroscopic quantity. And this makes sense because now we can also, with this macroscopic quantity, we can also take use of other macroscopic quantities. So for example, the photon flux, and these are something more easily calculated, that how a kind of like macroscopic a laser beam is hitting the medium, affecting, for example, the absorption. So how does sigma change when we go into a collection of states? That, in a way, is the kind of main question we would want to answer here. And what happens is that basically we are like transitioning our treatment for using delta functions into distributions. So we have seen before that for the case of a single atom, the cross-section is given by this kind of equality, so that the cross-section sigma is this kind of term times the delta function. And we can recall that the delta function is essentially defined that when we integrate over a frequency values, that's unity. And now what happens when we move our treatment to really concern multiple atoms, so a collection atoms, we just basically replace this delta function with a different function that has these properties, so that they kind of like when we kind of integrate this different function with respect to all the frequencies, we still get unity out. So something actually definitely happens, and that's the kind of reasoning we have here when we go to treatment of multiple atoms. So now we call this different function a line shape function, and we usually denote that with a G. Sorry about the confusion that the G seems to be used to describe multiple parameters, but in the end, this is the nature of physics. You just need to be getting used of the fact that the same kind of term is used to denote different things in physics. So here, essentially what we want, this line shape function G has the same properties as the delta function, so that we can really just replace all the delta functions in our piece of mathematics here with the line shape function G. So basically, like I already said, the G, we want it to have the properties that it's normalized when we integrate over all the frequencies, and basically that it peaks when the frequencies coincide. So these are the requirements for the line function for now. In what follows in the next lecture, we will go in more detail into the actual kind of like mathematics of these line functions. And of course, in this Swelto's book, you can find really explicit equations for different kinds of line functions. But this is basically the kind of main properties we want out of the mathematical structure for these line functions. So we want them to behave basically like delta functions. The explicit form of this line function really depends on the material and essentially on the kind of like the properties of the kind of medium and the environment. So basically that depends on the broadening process that the atoms undergo when they are being brought together. So it might be that when we are, for example, making a solid state gain medium, the line broadening is very much different than in the case of a gaseous medium and so forth. So when you're really like looking into kind of like particular lasing gain medium, like all the details of what happens under the hood within the microscopic kind of transition from a microscopic system into a macroscopic system, all of that is basically being hidden inside this line function. All of that ugly, non-trivial piece of mathematics describing a kind of complicated medium in a simplistic manner in terms of mathematics. And here below, I'm just trying to kind of show what can happen, for example, so that we may have several broadening mechanisms within our gain medium, so that the kind of total line shape function that I'm denoting here with the GT can be, for example, broadened both by so-called homogeneous broadening mechanism and also by inhomogeneous mechanism. So essentially, something like this may happen. So here I'm trying to draw with the red line, that's the kind of total line shape function, and then I have my kind of like a narrower line shape function, and basically this kind of like a homogeneous broadening taking place. So for example, if I would have a kind of like gaseous medium, this homogeneous broadening might be kind of like associated with the kind of like a single emitter, and then we have a Doppler broadening so that the kind of like atoms inside the gas can travel in different directions. So then subsequently the resonance frequency can broaden due to this kind of like a velocity distribution, and then ultimately the kind of total line shape function is a kind of convolution over different kinds of broadening mechanisms. So mathematically, this GT corresponds to a convolution of G line width function of individual atoms over the kind of distribution of atoms in what kind of states they can have and how they react to impinging field. So this is kind of like a starting point lecture to understand what happens in terms of cross-section. So we want to understand that how we can generalize a treatment of single atomic absorber and emitter into a kind of macroscopic laser gain medium, and then we realize that subsequently we are dealing with many atoms, so some kind of line broadening may start taking place within the absorption and also within the stimulated emission of our system. But I thank you for your time, and the next lecture will really be more about the kind of actual line broadening mechanisms. So please follow me quickly to listen on that video regarding follow-up of this material. So I thank you for your time and patience. Thanks. Bye-bye.